Good morning. Welcome to C++ Coroutines from scratch. Oh, actually, I started too soon. I meant to do this. So I've got to start in an initially suspended state. It will get better, don't worry. Actually, this is my real first slide, my title slide. You might recognize the bridge here, the Clifton Suspension Bridge, very famous, just around the corner. I took this photo just yesterday. I went for a run, and I was about 2 miles out, so it would have been a 4-mile round trip. And since the pandemic, I haven't actually run more than about 5K, so it's still really a bit further than usual. So I was thinking I should go back now. I was just crossing a bridge, and I could just see the one of the towers of the suspension bridge around the corner. I thought, if I just run to the next bridge, then I'll be around the corner and I can see the whole bridge and take a photo. And I wanted to do that because I wanted to point out all the suspension points. Sorry about that. Okay. But it also makes a good opening slide. So I'm Phil Nash. You can reach me on Twitter while that's still running. Otherwise, you can fall back to Mastodon. You may know me as a regular speaker here at the ACCU conference and other conferences, or as the original author of Catch, now Catch 2. More recently, taken over as co-host of CPP Cast. So I get about a bit. But I'm also developer advocate at Sonar. You can see my Sonar Lint t-shirt here. No, they wouldn't forgive me if I didn't wear this. So we do static analysis tools. Not going to be talking about that today here, but if you do want to speak to me about it, do feel free to catch me afterwards. I'll be here till tomorrow. Although, Sonar Lint will make a guest appearance towards the end of the talk, so watch out for that. It's quite fun, actually. But no, we're going to be talking about C++ coroutines, of course. Now, actually, who here, just to get this out of the way, who here is an expert in coroutines? Usually no hands, but Dietmar's gingerly putting his hand up. Yeah, there's not many. So if I'm making mistakes, you've got to stay quiet. Who here is at least comfortable enough that they think they can probably use it on a project, or they already are? So yeah, three or four hands, maybe. Or get your hand up if you haven't done a talk on it. Usually about half of those people have done talks. There's a few more people actually use them in the real world now. That's good. But who here has seen at least one other talk on coroutines or read at least one article on coroutines, still doesn't quite get it? Right, yeah, about half the room. That's normal. In fact, actually, who here has seen at least one other talk on coroutines this week? Yeah, there's been a few. But why is that? Why does it take a few runs at it to get this? A few reasons, actually. Partly, it is just a complicated or a complex subject to start with. It's a complex solution to a complex problem. Not super complex. Actually, it appears more complex than it is to begin with. That's part of the problem. There's like a steep learning curve, and then it drops off quite quickly. But it is a lot to get your head around to begin with. And that, of course, is made worse by the fact that we're doing this in C++. And we have C++'s take on coroutines. So if you view coroutines in another language, and then you come to C++'s version, and you think, why have I got all this extra stuff to think about? And part of the reason for that is actually it's a lower level facility. It actually gives us more flexibility. There's more things you can do with it than most other languages that have coroutine facilities. So that's a good thing. But the idea was we're actually meant to get library facilities that will help to make that a bit easier to work with and practice, and we're not quite there yet. We're starting to get some. We'll talk a bit about that later. But for the moment, you've got to build lots of stuff yourself, do lots of boilerplate. And there's just lots of moving parts, and it can be overwhelming taking that all in one go. So if you've seen one talk, you can understand individual bits and you just have trouble keeping it all together. So it takes a few rounds to get through that. So I'm actually going to take advantage of that phenomenon and do something a little bit risky. Because one thing I noticed was many other coroutine tutorials and talks and things, they'll start with a really simple example, because you don't want to be too distracted by the complexity of the problem. You want to focus on what coroutines brings, which is exactly the right way to do it. That's not what I'm going to do. Because sometimes the side effect of that is you can come away thinking, that was a really complex solution to a simple problem. And maybe you think that's what it's all about. But no, when you have a good match of complexity, that's when you really start to see the value in using coroutines and actually putting the investment into learning them. So that's what I'm going to try to do here. But the risk is, of course, trying to cram that into a single talk. I've got to actually spend about half of the talk basically explaining the problem and some initial runs at it before we actually get to coroutines. And I may lose you along the way. So that is the risk. I've done this a few times now, and I've been bringing more people along each time, so hopefully we'll get there. So what is the problem we're going to be talking about? This is actually based on a real-world example that I had, the last full-time development job I had years ago. We had a problem that was a great fit for coroutines, but we just didn't have them then. We really wanted them, so when coroutines actually came around, I was thinking back on that. I thought that'd be a good problem to talk about. So at the time, I was working in finance on a quant library. If you've never looked at quant libraries before, know nothing about this, don't worry. You can just think of these as names. We're not going to look into any of the calculation side. In fact, we're just going to be talking about data serialization today. But I'm going to use these names just so it gives it a bit of a real-world feel as well. You can actually think, no, this is the real problem we're dealing with here. So these are some of the types that we dealt with. Let's say, don't worry about the names themselves. In fact, we're only going to really deal with these ones today. And they're just there to give it a bit of flavor. I said it's a serialization problem. It's actually more of a deserialization problem. And what's more interesting about these is the structure of the data. So this is one of those objects. You can see it has a number of value members. Even the vectors are just vectors of values. So this one's quite a simple, straightforward one. Although do notice that we derive from this, I'm just calling it F object. The quant library I worked on, like many quant libraries, still have these sort of singly rooted virtual hierarchies. This is no different. So everything's an F object in this case. Slightly more complex one, forward in this case. This has a load of value types, but also these shared pointers here. These are our dependencies. So you'll see a lot of this. You actually build up these big object graphs of objects with interdependencies and many shared dependencies as well. So shared pointers everywhere. Still very common even today, I understand, in quant libraries. And you probably worked on something similar yourself in some other domain. Hopefully you should understand what we're doing here. Actually, these curves, they're also sort of the base of a little polymorphic sub-hierarchy as well. So we have a number of different curve types as well. Flat forward, fitted bond discount curve, we're going to see these. So we've got that sort of thing going on as well. Forget why I put that one in. Oh, it's just another little sub-hierarchy. Okay, deserialization then. We're going to have a load of JSON files like this that have values, or in some cases, like these curves, they're actually the names of dependencies to load. And I think we've got, that's just highlighting the dependencies. If we're loading a curve, the JSON will get back, just tells us what the actual instance is. So we've got to do like an extra hop to get the actual curve data as well. So there's a few little, extra bits of complexity in the problem. But that's it, I promise. That's the limit of it now. So we've got all these JSON files. We're going to want to get a couple of objects, and we're going to have to load all the dependencies as well and work them all out as we go. That's the problem we're trying to solve. So more concretely, these are the two objects we want to load for our specific example. So two fixed rate bond forwards. So don't worry about what that means. They're just the high-level objects. Now, to load these two, if you map out all the dependencies, this is what we're going to end up actually loading into our object graph. So there's 10 objects here. Not all of them make it into the final graph. Those curves with the dotted lines, they're just those like extra hop objects that we need to load to get the final ones. So we'll end up, I think, with seven objects in our graph in the end. This is our main. Oh, well, I should say, first of all, we're going to look at three code examples. Well, they're all evolutions of the same code base. Main is going to be exactly the same in each one. So I'll spend a few moments talking about it here, and then it'll just be the same. Pretty straightforward. So we'll get to repo in a moment. You can then see we've got this clock. We're going to do some timing. We're going to just see how long it takes to build these objects. Printed out in milliseconds. That is going to be granular enough for reasons that will become obvious, hopefully. And the main part is we're going to load and build objects into our repo. So the loading is just loading the JSON in, and then building is serializing that into objects and resolving all the dependencies. So by the end of that, we'll have all of our objects in the object graph, including the ones we asked for. And then just a little smoke test at the end to give us some confidence that we actually loaded what we thought we were going to load. I'm just doing a bit of, we take one of the objects that we loaded, the second one there. We happen to know, well, we know because that's what we asked for. It's a fixed rate bond forward, so we cast it to that. And then from that, we can pull out a discount curve, one of our polymorphic dependencies. We happen to know from the data that that's a fitted bond discount curve, so we'll cast it up. And finally, pull out a value from that. So by no means exhaustive, but it gives us some idea that we've probably loaded what we thought we were going to load. So that's it. And in fact, I can run that. And if I scroll that up a bit, should see, here we go, it's printed out the time. 123 milliseconds, so milliseconds was enough. So it seems quite long just to load 10 objects. We'll see why in a little while. So let's dig into this a bit. So let's have a look at the repo first of all. Pretty simple, only has one data member, this map from string to f object. Remember, all of our objects in the graph are f objects. So every time we load something and build it, we stick it in the cache and key it by the ID that we use to load it. That's it. We've got this load helper function we'll look at in a moment. And then that load and build objects that we called. So not much to it. So let's have a look in here. So these are the IDs that we asked for. Those IDs, by the way, that's just what I'm calling that sort of type name / some identifier. So everything's uniquely identified that way. So we're going to return a vector of f objects. We know how many, so we can reserve that up front. Nothing clever there. Iterate through our IDs that we passed in. See if they're already in the cache, because they may be. And if so, we can put that straight in our output vector. Otherwise, we call our load, and what that returns, we put in our output vector. Hopefully, again, pretty straightforward. Load is passing off most of the work to deserialize. We'll look at that next. And when it gets back, it just puts in the cache. That's the only extra thing it's doing. So it's called deserialize now. A little bit more here, but most of this is just this big type switch, which I've sort of unrolled here. I wouldn't normally do it this way. You probably want some sort of map of ID to some sort of factory method, but with just a few types, it's just easier to show it this way. Because the first thing that we get in from our JSON is the type. So now we need to know what object do we create and how do we deserialize it. So we have all these builders we'll look at in a moment to do that. And then separately, those curves, because they're a bit special, they only have that instance value. So we're just going to read that and say, oh, that's the type, and then recursively call back to deserialize to load the actual curve. All right, let's have a look at the builder for fitted bond discount curve. Because this is actually the simplest one. It's got the longest name, but it's the simplest type. It only has, it's the leaf object, so it only has values. Sorry about all these pop-ups. So we're just deserializing values out of the JSON straight into the object. Pretty straightforward, okay. But if we go up here, slightly more complex, fixed rate bond forward, this one has dependencies. So after creating it, getting one value out, we then, there may be others, but we then go straight into loading our dependencies. We're going to call back on the repo, load and build objects. If you remember, right back up in main, we did this. It's the same call, but now for our dependencies, which means we've had to pass through repo all the way down to here so that we can do that. So we've got very tight coupling in this. The repo knows about the deserializer, the deserializer know about the repo. It simplifies this particular aspect of it, but it has its own problems. But at the end of that call, we should have all our dependencies loaded, so we can now set them into our object, and we're done. So a little bit more complex, but still not too bad, I hope. Again, it's not to do with coroutines just yet, so you have to keep bearing with me. And I think that's all we need to look at here for now. So I'll run that again. So there's two problems with this approach. One is this figure here. Because, so we're going to look at why it takes so long to load. That's the bit I didn't show you, actually. The bit that actually loads the JSON, I put this sleep in here. But the reason I've done that is because I'm loading this from files locally on my SSD. But actually, in practice, you'll probably be loading this across a network from some data store. And that's going to have some latency for that round trip. So we're going to pay the cost of that latency every time we load another object, which in this case is 10 objects. So 10 times 10 milliseconds, 100 milliseconds, gone just on those sleeps. That's mostly what we're timing here. And that's, you can argue over whether 10 milliseconds is representative these days. Networks are getting pretty fast, but it's still going to be our bottleneck, I think. So the thing is, if we go back to the slides for a moment. Right. So these are the objects we're loading, our 10 objects. But we already know the first two up front. We know we wanted these fixed rate bond forwards. And then we can ask, once we've got the data back for those, we can ask them, even before they're fully built, what their dependencies are. And we get back another 5, I think, objects. 5 names, rather, of objects, which we can then load in another batch and then ask them for their final 3 dependencies. So actually, we can end up with something like this. So basically just shifting from a depth-first traversal to a breadth-first. Get as many dependencies as we can at a time and batch them up. Now we've only got 3 round trips. And we should only pay that latency cost 3 times in the idealized case. So this is what we want to move towards. So nothing particularly novel about this. I'm sure we've done similar things many times before. But let's see what that looks like in this particular code base. So, second example is at the top here. Sorry, I need to switch that. There we go. Right. This is our second example. As I said before, main is exactly the same. This hasn't changed at all. Let's have a look at repo, though. This now has changed a little bit. We've still got our cache as before, but we've now also got this vector of strings. This is going to be our next batch of IDs to load. So we're going to keep populating this and then loading them, populating and loading. And then we have 2 new helper methods we'll look at in a moment. In fact, require object we can look at now. That's quite simple. Anytime you need an object, you call this and it's going to look it up in the cache, and if it's not there, it will put it on to load. That's all it's doing. Resolve dependencies is a little bit more involved. We'll look at that in context in a moment. So let's go to our load and build objects. And we can see this already looks a lot more involved, but it's not too bad. Let's break it down. So we've got our initializer list of IDs coming in, as before. But now we want to batch things. We want to immediately put that in our to load vector. So that's all this line is doing. And we're doing it using the require object, just in case we've already cached them. So that will end up with both of those IDs the first time around being in there. We'll look at incomplete tasks in a second. We're then going to go into this loop. All the time there are more things to load, so we may go around this a few times. In fact, we know in this example, we're going to go around 3 times. And now we have a batch version of our deserialize function. So deserialize all takes a vector of IDs now. We'll get to that. And we can clear down our to load vector, ready for it to be populated again. But deserialize all returns not the objects, but these things I'm calling build tasks. So what are these? Well, because our object's going to be in partially built states now, and we're going to have this extra dependency information that we need to manage, that's what we're holding in these build tasks. It's a partially built object, and it's outstanding dependencies, so that we can then wire things up and complete the build. So it's sort of like an ongoing build task. So what we're going to do is iterate those build tasks and see if we can resolve them now. Because if it's a leaf object, it has no dependencies. Or if it has some dependencies that we already have, then we can resolve them straight away. So that's what we'll do in resolve dependencies, which we'll look at next. And if it's not resolved now, we'll put it in that incomplete tasks vector so that we can come back to it later. But in fact, let's look at that next. Because after we've been around this loop a few times, well, we should have loaded all the objects and we can finally go through our incomplete tasks vector in reverse. So we go from the most dependent to least dependent objects and just call resolve dependencies on those again. And because we've got everything now, that should all resolve and we'll have all of our objects. Don't worry if you didn't follow that completely. You can trust me on that one. And finally, all we need to do is just look those objects up in the cache. They should all be there now, and we can put it in our output vector. So let's have a look at that resolve dependencies, which is doing a lot of this work. So for a particular build task, we can ask it for its dependencies. As I said, that's what's keeping track of them. And it may already be met, because we may have been around this before. But if it's not, we're going to call that require object. If you remember that, looks it up in the cache first, so it may already have it, in which case we can supply that immediately. And if not, then we have an unresolved, an unmet dependency. And we need to keep track of that, because if we don't have any unmet dependencies, then we are now resolved. And so we can call task.resume. Well, we'll look at that in a second. Put our object in the cache and just say, yes, we're resolved. So let's have a look at that task.resume. Because once an object has all its dependencies, it may still need to do a bit more work to be fully built. So we have some way of having this, some sort of continuation callable to complete that work. So if it has one, we'll call it, reset it, and then we'll either way return the object. So that's all our resume is doing. We'll look at that from the other side in a moment, and maybe that will make a bit more sense. So at the end of this function, either we have a resolved object, all the dependencies are wired up, or we don't yet. We'll come back again later. So that's our load and build objects loop. Let's have a look into our deserialize all now. So as before, well, not as before, this is now taking a vector of IDs and returning a vector of build tasks. But we've put our sleep to the outside the loop, so only once per batch. That's what we wanted. We know how many build tasks, so we can reserve that up front. Now we're going to loop through our IDs, load the JSON as before, and call build object. So let's have a look at that. And this looks fairly familiar. It's what we had before the big type switch. Most of this is unchanged, except that curve is now treated the same way as the others. So we just have another builder for curve. Let's look at the builder for that simple one, fit upon discount curve. This looks almost identical to what we had before, because mostly we're just deserializing data, straightforward. We return the object as before, but the return value, the return type, sorry, is build task. So build task has a constructor that can take an object, but it can also have an unbuilt object. It can work both ways. Let's have a look at the more complex case, the fixed rate bond forward. This is the one that has dependencies. And you can see we're actually treating those a bit differently here. We've got a dependencies object that we use for tracking those. So we call require for each dependency and pass it the field that we actually want to populate with the dependency when we have it, and the name of the field in our JSON that we're going to get it from. So internally, it can keep track of all that. And then that's all tracked by our dependencies object. And then it gets more complex down here. Because now we're saying, these are my dependencies. I can't do anything else until you give me those. So I'm just going to finish up with this function, this method, and call me back with this lambda when they're ready. Now, if you've done any sort of async code before, or any sort of callback code, we're not really doing anything that different here. It's always that little bit complex. At least got easier when we've got lambdas. When I was originally doing this, we didn't even have those. We had to have separate objects for it. But hopefully this should in general be fairly familiar to you. We have extra complexities like we have to move the object that we're building in so that we can keep building it. But what we're saying is this build task, we're going to continue once we have those dependencies. And we're not actually doing anything extra in here, but we could do. And then we return the object. So I hope that makes some sense. One final thing I want to show you here, though, is the builder for curve. So we're treating it like the other objects now. The instance now becomes a dependency, so the actual curve that we want. But we have this intermediate object that we need. And so we have this abomination here. A shared pointer to a shared pointer. Why would we do that? We actually just want the shared pointer that's going to be the final dependency, the final curve. But because we're not going to get it until we get into this lambda, we need something with a stable address in the meantime that we can hang on to and pass in, this curve holder. So you can see we're moving it in here. But we need to be able to write to the address of the actual shared pointer. So that's why we have to have another heap allocation, put it in another shared pointer, move that in. And then finally, we can throw that all away and just get the original shared pointer that we wanted out and return that. If that didn't make sense, don't worry too much. It's not essential to understanding it. The main point is because of this style, we've had to jump through some extra hoops, maybe with extra allocations, just to keep things in memory. Because really what we wanted to do was just write some linear code from here to here, but we've had to break it up across calls and keep track of some of that information. That's really what I'm trying to demonstrate here. All right, so fair bit of extra complexity. Oh, I didn't even get to the build task yet. Let's finish up by looking in there. So this is the thing that's going to track our partially built object and its dependencies. Now, because I want to be able to pass these build tasks around, give it some sort of move semantics, we're actually putting all the data in a separate class or struct called data, and we've got a unique pointer to it. So we've got unique ownership semantics. So all of the data is in there. We've got our ID, the dependencies, the object we're building, and that continuation, which you can now see is just a std function, returns an f object pointer. That's what's going to hold our lambda. Most of the rest of it is just sort of bookkeeping, shuffling bits of data around, and this resume method. So that's the thing that we called from resolve dependencies earlier. So we already looked at that. So It's going to call the dependency continuation if it's there. Otherwise, just return the object directly. Okay. So individually, I think all the bits hopefully make sense, but definitely a lot more complex than the first example. What's the payoff, though? If we run that, should run it a few times to warm it up. So typically around 36 milliseconds to run. So more than 3 times faster than the first example, which is what we would expect, given what we know about those sleeps. But it's nice to see it in figures. Now, in an application like a quant library, that's obviously really important to run 3 times or 4 times faster or more. And in many applications, of course, if we're using C++, it's very often because we want performance. So we're willing to pay the cost of this extra complexity to get that, especially if it's so significant. But it is a shame we've had to add all that extra complexity in. So let's go to jumping ahead. Okay. Let's introduce coroutines, finally. I said we'd be halfway in. We're not quite at a halfway point yet, so we're a little bit ahead. Good. So there's a few things. So there's lots of moving parts to coroutines. I'm going to try to introduce them gradually, but at some point, you may get overwhelmed if you are not already familiar with them. If you've seen other talks, maybe this is the point that they start to make sense. Let's see. I divide them into 2 broad categories. The things that we provide over on the left, and the things that the standard provides over on the right. There's some more things coming in here in a moment, and we'll drill into some of these in a little bit more detail. I actually want to start with a part that doesn't have a type, at least not one that we have access to. I think it's maybe the most crucial part to really understanding how coroutines work, and that's the coroutine frame. So you can see there's no actual types involved there. And it spans both sides as well. That's also important. So the coroutine frame is really just the block of memory that gets allocated when you create a coroutine. That's that heap allocation that it may be possible to elide. It's also loosely equivalent to the stack in a non-coroutine routine, but not exactly, because there's extra stuff going on here. So the only way we can access the coroutine frame is with a coroutine handle, which the compiler will give to us, or the library will give to us. But we actually have something living in there, and that's this promise type. Don't get too hung up on the name. It has very little to do with std promise. I mean, the conceptual underpinnings maybe, but very different purpose here. The promise type is really just a place in the coroutine frame that we can put our stuff. If you think of it that way, that's actually a much more useful way to think about it. So we can put our stuff in there to do with just the running of the coroutine, bits that we're moving in and out. The other thing that goes in the coroutine frame is all of the local storage variables in your coroutine function. So things you would normally think of as being on the stack, or your local variables, by value arguments, that sort of thing. They all live in the coroutine frame now. And there's some implications to that, which are quite interesting. So we'll revisit that. And there may be some other little bookkeeping bits that you don't even get to see. So we won't talk about those. So that's the coroutine frame. We'll dig into the promise type a bit more in a moment. Now let's have a look at the objects over this side, which we'll also dig into a bit more. But first of all, it's worth noting that the coroutine handle manages the coroutine frame, but it's not itself an RAI type. So it has a destroy method on it, which will tear down the coroutine frame. You have to explicitly call that at the right time. And usually, doesn't have to be, usually it's our task or generator type that's going to do that. So the task or generator type will get given, actually you have a choice here, but we usually get given a coroutine handle and then you have to manage it. So what is the task or generator type? And why is it so awkwardly named? We don't really have a decent generic name for this one. I've also seen it called the future type, the coroutine future type. That's even more confusing for the same reason that the promise type is confusing. Again, it's not the same as stood future, conceptually maybe. I like to think of it as our remote control for the coroutine machinery. And it's the place that we can define our interface onto our coroutines. So right now, at least, this is very much something that we write, but it could also be provided by a library. And we will see, and we are going to get stood generator in C++ 23. We'll talk about that later. But yeah, this is your sort of user space interface to all of the coroutine machinery. We'll see that in a bit more detail shortly. Talked about managing lifetime. To get to the promise type, though, it's a little bit subtle because very often you'll see the promise type defined within your task type, but it doesn't actually directly have an instance of the promise type. Remember, the promise type always lives in the coroutine frame. It's created for you and managed by the coroutine handle, but you can get to it via the coroutine handle. So to get to the promise type, you go via the coroutine handle. Now, the awaiter, we haven't talked about yet, also gets given coroutine handles at different times. And we'll look at the definition of that in a moment, but it's worth noting there are two specialized types of awaiters provided by the standard library that are very useful. You see them a lot. You wouldn't even think of them as awaiters. You can think of them just as meaning suspend always and suspend never, but they are actually awaiters, which means you can use your own custom awaiters where you would see these, if that makes sense. So one of the roles of the awaiter is to say whether the thing you're waiting for is already ready. So if you get to a point, like in our example, where you're saying, I want to await these dependencies. If those dependencies are already ready, you could actually potentially continue there and then. You don't need to suspend. So the awaiter gets a chance up front to say, are you ready? And if so, it doesn't suspend. So suspend never always returns true for that it is ready. And suspend always returns false. And that's really the only difference. And because they are const expra, the compiler knows all this at compile time. And so if you use these types, then it can reason about how the coroutine works at compile time and optimize that a bit. So always use these if they make sense. You'll see them a lot. Two other types, honorable mention. We're not going to talk about them much. Not going to talk about not coroutine promise at all. Don't worry about that for now. Coroutine traits, you don't often need that. But you can think of that as just a way of configuring certain things, mapping certain things. But we're not going to talk about that too much either. All right, let's dig into the task type a little bit more. So I said you will usually define the promise type within the task type. By default, the coroutine machinery will expect to find promise type within your task type definition. Whether that's directly there, directly defined there, or whether it's defined somewhere else and you just have a using statement in there, or a using declaration. You can also use those coroutine traits we just mentioned to map to some completely different type. That may also be a more convenient way to do it. Don't worry too much about that. It doesn't come up very often. One curiosity here is that the task type knows about the promise type one way or another. And the promise type knows about the task type. And you have this like interdependency. And one way or another, you're going to have some sort of forward declaration to resolve that. It's just something you have to deal with. Not that big a deal. The task itself rarely has any of its own state. It probably shouldn't. All of the state that you want to hold on to while a coroutine is running you should put in the promise type. You have access to that. But you don't have an instance directly. What you do have an instance of, usually, is the coroutine handle, which, as we said, we can get access to the promise type, and we can also control the coroutine. We can resume it, we can destroy it, we can do a number of other things, including getting to the promise type. So the promise type then. As I said already that this is where you can put all of your state to do with the coroutine, and that's going to live on the coroutine frame. But it's particularly important for being how the coroutine machinery interacts with you by using these member functions. There's a couple of others as well. We'll get to those in a moment. So, although these are functions you provide, they represent an interface that is required by the coroutines. So get return object. It's going to be easy to see this in practice. We will in a moment. But you can think of this as just the thing that creates the task object for now, like a factory for the task or generator type. It almost always has the same implementation. You can almost copy and paste it most of the time. But we'll look at that anyway. Initial suspend and final suspend are pretty straightforward, but it's worth spending a moment or two talking about these. So your coroutine, we never really talked about what a coroutine is. I've left that to other talks. But you can, as well as running a coroutine, you can suspend it and resume it. I'm sure we know that. But when you create the coroutine, does it start in a suspended state, or does it run a bit until it gets to the first co-await, co-yield, or co-return? And that's what initial suspend tells you. I would say more often than not, it makes sense to not initially suspend, so immediately start running until it gets to that first suspension point. But there are many valid cases where the opposite is true. You can only just look at your particular problem and see what makes sense. And usually you will know that statically, and so you can use one of those trivially awaitable types, like suspend never, as the return type, and then it's known at compile time. Final suspend, I would say 95% of the time, you should say suspend always. So to first approximation, always suspend always for final suspend. The reason is your task or generator type is usually managing the lifetime of the coroutine via the coroutine handle. If the coroutine doesn't complete in a suspended state, that means it's gone away. You no longer have access to it. And you don't know exactly what that point is going to happen unless you know exactly how things interact. So it's very difficult to manage things correctly if your coroutine doesn't complete in a suspended state. So why would you ever do it? Usually it's because coroutines are actually executing on different threads, and you don't know the point that the last one finishes, and it has to clean itself up. It's not something I've really explored that much yet, so I can't tell you more than that. There are other talks that will go into that in more depth, so I'll defer you to them. But most of the time, unless you know otherwise, final suspend should be suspend always. Your coroutine completes, it's done, but it's still there in a suspended state and you destroy it. That's the usual way. So that's initial suspend and final suspend. The next member functions come in pairs. So either return value or return void. Now, because coroutines are a bit weird in that from the outside, you call it and you get back a task object. That seems to be the return type. In fact, to get return object, it's talking about that return. But from within the coroutine body, you want to return something, you co-return it. But you can't use the usual return channel for that. So it has to call into the promise type with that value. So if you co-return some x, you're going to get return value x. And if you co-return nothing or drop off the end, it's going to call return void. So fairly straightforward. Because these are not, virtual functions, there are not strictly defined interfaces. As long as you spell them correctly, you can take any type of value category. You can take it by const reference or by R value reference, whatever makes sense. It can even be a template. And this will typically only be called once, of course, but it may be with different values. So because you get called with the return value, then it's your responsibility in the promise type to store that within the promise type so you can later retrieve it. And remember, that all goes into the coroutine frame. So that's return value and return void. So all of these are mandatory. You have to provide these. The next two are optional in different ways. Yield value is optional in the sense you only need it if you have a co-yield in your coroutine. And otherwise, it's going to behave exactly the same way as return value. So when you co-yield a value in the coroutine, it's going to call yield value on your promise type with that value. Again, any value category, or it can be a template. And you can have multiple co-yields with different types. So if you need to hold on to that value, you store it in the promise type. Unhandled exception is maybe obviously if you have an exception thrown from the coroutine that escapes the coroutine, well, it's going to call unhandled exception with that exception pointer. And you can do something with it, or you can do what all of the demos do and just terminate. In a real application, you might want to do something a little bit more involved, but I'm going to continue the tradition in this example. Not going to dig into that too much. Okay. So yeah, this is the big one that's usually a bit overwhelming. Hopefully I've broken it down a little bit, but it'll make more sense when we look at the code. The awaiter is a bit smaller. Has these three methods. We've already looked at one, actually. We talked about await ready. So this is the one that up front gets called to say whether the coroutine should suspend or not. Is it ready? If not, it's going to suspend. If it does suspend, then it will call await suspend with a coroutine handle. And you can do something in there. You don't have to. In fact, in this example, we're just going to log there. But that sometimes can be a very important function. And in fact, you can make different choices about what's going to happen next. I'm not going to dig into it too much today, but you may have seen in other material that the return type of await suspend is significant. And different return types can signify different things to the coroutine. That's a little bit more advanced than I'm going to get into today. Await resume gets called just before you resume again with the coroutine handle. So that's all I'm going to get into for the moment. Wanted to now show you that in the code. So go back here. And here, okay. So our third example. So now we've added coroutines. Main is exactly the same as before. Have a look at the repo, and it's exactly the same. At least at this level. If we go to load and build objects, there was a lot going on here that we changed for the previous example. This is now almost exactly the same. There's just two lines that have changed a little bit, those two. We'll come back to that a bit later. But for all intents and purposes, you can think of this as unchanged. In fact, we could have written this in a way that we didn't have to change this at all. So that's good, because that was a complex bit. And resolve dependencies is also unchanged. So almost nothing in repo has changed in order to facilitate the use of coroutines here. All right, let's dig a bit deeper. Have a look in deserialize all. A few changes here. Broadly similar, but let's go into this. So we've got the sleep up front as before. We are now creating all our deserializers up front rather than doing them one at a time. And that's all that's doing, loading all the JSON up front. We could have done that before, but it wasn't necessary. And then we're going to go through our IDs, and for each of those deserializers, call build object. And then you can see down here, now we've got a co-yield. So we'll come back to that. I'm going to suspend for the moment and dig into build object. So build object itself is unchanged. We've got our type switch as before. Let's have a look at the builder for fitted bond discount curve. Remember, this is our simple one. If you look at the body of the code, this is unchanged except that we're now using co-return instead of return. If you've seen any other coroutine talks, you'll probably remember that what makes a coroutine is the presence of one of these co-underscore keywords. Co-return, co-await, or co-yield. It's not actually the return type, but the presence of these keywords. You have to look in the body to know. So this is a coroutine, and so is the deserialize all, a different coroutine. All right, well, we'll come back to that in a moment, but let's have a look at the more complex example. The builder for fixed rate bond forward. And it's very similar, again, up to here. We're building our dependencies object. But then we do co-await dependencies. So this is a bit where we're saying we're going to wait for the dependencies and we're going to yield out until they're ready and then resume. But let's compare that to, if I can find it now. Further than I wanted to go. Okay. Here's the equivalent we had before. We had that build task with continuous dependencies and the lambda and moving stuff in. Now, we just co-await dependencies and co-return our object and any other code we want in between. I think you'll agree this part, at least, is a lot simpler. And I think more readable, more meaningful. But what's actually happening here? So our build task, we're going to look at that in a moment. It's actually somewhat similar to what we had before, but this is now our coroutine task object. So that's what gets returned there. So when we co-await dependencies, we are saying, with this dependencies object, I want to wait until they are ready. And then when they are, please resume this coroutine from this point. And everything that was on the stack, or the conceptual stack before, actually the coroutine frame, is actually still around. We haven't had to do any moves or new allocations or anything, it's just there. We continue on with linear code until we get to co-return. And that co-return is going to call return value on your promise type. And just to drill that home, let's have a look at the builder for curve. Remember, this is the one where we had to create that shared pointer to a shared pointer. So we have that stable address in memory. We don't have to do that now. Because now when we declare our curve here, it's sitting in the coroutine frame. Which means after we await for dependencies, we get suspended and resumed, we're still in the same coroutine frame. It's still sitting there at the same address. We can just use it directly and co-return it at the end. Which means this is a lot simpler, nicer, more natural, easier to follow, easier to debug, everything. It's much nicer. And probably more performant as well. But I haven't measured that. All right, let's dig into this a little bit more then. Build task. So this is now a coroutine task object. Don't worry about the base type, that's just for logging. If you remember before, our build task had this embedded data object. I said it was just there so that we could move the state around. Well, promise type is now taking that role. A slightly different way, but it holds our state as we did before. And then it's got all of our coroutine invoked methods that we saw on that previous slide. Actually, there's one extra one, which I'll come to. So let's have a look at these now in the code. So get return object. Remember, this is the thing that actually creates our task object. It's a little bit weird that it's sitting here within the promise type, which itself is within the task object, but that's how this works. Usually, you're going to see an implementation like this. So our build task needs a coroutine handle. We can get the coroutine handle from the promise, which is us, by calling handle from promise. Or handle is just a using of coroutine handle promise type, by the way. So again, 9 times out of 10, that's what you're going to see to get return object. You don't have to do it that way, but that's what you'll mostly see. Initial suspend never. So we will start the coroutine running until we hit the first suspension point. Final suspend always. Remember, always suspend always from final suspend, unless you know otherwise. And then return value, because we have a co-return. Takes an object by our value reference. Like I say, you get to choose the value category, whatever makes sense. And we are just squirreling that away in our promise type up here. And a bit of logging. We'll come back to await transform. We have unhandled exception, as promised. That's going to terminate, so hopefully nothing goes wrong. I'll leave filling that out as an exercise for later. All right, await transform. I didn't talk about that one before because this is an optional, definitely an optional one. This is to do with what you can await on. So the thing you await on has to have that awaiter interface that we looked at. But dependencies doesn't have that interface. It could do because we own the code, but often you want to keep those separate or you don't own the type. It makes sense to have a different type to do the awaiting. So we can't put that interface on there directly. So you can either use await transform to say, if you give me dependencies, then we'll create this dependency awaiter in this case. You can also do it with the co-await operator keyword. And I think there might be something in the coroutine traits that will let you map it as well. But this is the usual way. So you either implement it directly or you supply await transform. They're usually the easiest ways to do it. Just to make that a bit more concrete, if I go back here. So this builder, we create a dependencies object and we call co-await on dependencies. That's going to invoke await transform with those dependencies. And if we look in there, that just stores the dependencies passed in and creates a dependency awaiter. In this case, our dependency awaiter is very straightforward. The only thing I really do is say whether it should suspend or not. If you passed in no dependencies, it doesn't need to suspend. So it will never actually suspend in that case. And the rest is just doing logging. As I say, this can actually be a lot more sophisticated and very often is. So you get past the coroutine handle in await suspend. You can do something with that. You can also, although I'm returning a ball here, you can actually return, I think, a coroutine handle as well. But I'm not going to dig too much into that today. So that's await transform. And that is our promise type. Remember, all of these live in the coroutine frame. That also means that whereas before, with the callback version, where we passed in dependencies, we then had to move that into a member variable. Here we're actually just taking a span of the dependencies because the original object is still living there in the coroutine frame. Again, we can rely on that still being there, if you're careful. The rest of build task, apart from managing the coroutine, I've got destroy here to call handle.destroy, if we still own it, and just adding some move semantics. The rest of it is pretty much the same as it was before. It's just our interface to the task. Obviously, resume plays the same role, but now it forwards on to handle.resume, resume the actual coroutine rather than invoking our continuation. And it gets the promise type, the object out of the promise type rather than our data member. But other than that, it's very similar. And obviously, I deliberately designed that build task to be a close enough match to coroutines that I could say that. It wouldn't always be the case. But I think it was a reasonable design still. You can see the reasonable design would be close to coroutines. So we didn't actually add much complexity, if any, to our infrastructure layer. But we significantly reduced the complexity in the builder code. Let's go back to that and look at that again. So here, we only have a handful of builders. In the real world code that I worked on all those years ago, that this is based on, we had dozens, if not hundreds of these. So the application code that uses this stuff all over the place is much simpler. It's similar in complexity to that original depth first recursive example, but without the depth first or the recursion. So conceptually simpler, the code is as simple, and we get all these benefits for almost no extra complexity cost once you've already bought into the extra complexity of that infrastructure layer. So whether you followed all the details or not, hopefully you'll at least have that takeaway. But this is actually a really good match in complexity for the problem at hand and gives you some quite significant benefits. There was a bit I needed to go back to. I'll come back here, I think. Deserialize all. Remember we said this is also a coroutine. In fact, as you can see from the name here, generator, particular type of coroutine. So generators only have co-yield, and they're called generators because they just generate values lazily. But otherwise, they act like a range-based interface, typically. In this case, it's not strictly range-based. So if we have a look here, you can see our familiar set of functions. We've got yield value and return void, but otherwise, very similar. We've got all the coroutine handle state management as before. Then our specific interface, we've got has value, current task, and next. And this allows us to effectively iterate through our lazily generated build tasks. There was no particular advantage to doing this as a coroutine other than for me to demonstrate this. Now, this is a fairly simple interface, but that does mean that in the load and build objects, we had to do this instead of just our range-based for loop. What I could have done, and I had actually meant to, but I ran out of time, is add an iterator interface to that generator. So actually, go back to here. So instead of these, we'd have an iterator interface. And that's fairly easy to do. And that would then mean that we wouldn't have had to change that infrastructure layer at all. It would be exactly the same as our previous example. It would also mean that using those generators would be really easy. You just stick them in a for loop and you're done. Or however you would normally use iterators. Pass them to an algorithm, whatever you want. And in fact, if we look at the generator again, there's actually, apart from the type name, pretty much nothing in there that is specific to our particular problem. Nicely generalizes. And of course, if you generalize, you want to do a bit more polishing, and that's what the committee were doing over the years. But finally, we got std generate into C++23, which does all of that and more, obviously a bit nicer. which means with C++23, we wouldn't need any of this code. Instead, our serializing task, sorry, get back to that point, here, we'll just say std generate of build task. And that's it, we're done. We can co-yield, here, range-based for loop on the outside, and it's nice and simple and it works. So opposite way around to most of these presentations, I've left the simplest bit for last. But hopefully that gives you a greater appreciation of what that's doing for you. But there is a problem here. It's a rather nasty one, actually. If I run this, you'll see. It actually crashes. And we've got all these like empty moved from states in the log. Yeah, really nasty one to try and debug. I genuinely hit this bug. Not the first time I wrote it, but when I went back to refactor my first version, I thought, oh, I can change this vector of strings that I was passing by value for some reason to pass by const ref. And then I hit this problem. I thought, oh, of course. Now you can see that it's highlighted here. Just say that sololint will make an appearance. This actually saved me in the end. Telling me to pass this by value because it may be used after the coroutine is suspended. It may become dangling. So yes, with coroutines, we can suspend on the way in as well as on the way out now. What do I actually mean by this? So if we pass it in by reference to something that's on the stack just above it at the call site, it's fine until you get down to here. And then we suspend. We'll go back to the caller. It will carry on. That object goes out of scope. Then we're going to resume, go back around this loop, and refer to IDs again. And now it's dangling. But this is a new way to shoot yourself in the foot. So that's why I wanted to highlight that. You don't have to use sololint, but use something that's going to catch this sort of thing, because it's very easy to get unstuck. Interestingly, if I put a break after that co-yield, then it's not going to actually refer to IDs again after that yield. And in theory, there we go, the highlight goes away. So that's actually okay. It might be a little bit dangerous. In general, I would recommend always passing arguments to a coroutine by value, unless you really, really know otherwise that is both safe to do and necessary. Be very careful. Okay. That is the end of my code example. So let me go back here. On the next slide. Okay, which is actually just this one again, except that I put a link to a page on my website, so levelofndirection.com/refs/coroutines.html. That has a list of a load of references and other talks, which I need to add to, but I'll get to that. There's some there now. All the reference material for this talk you can find on that page. So that can be useful, and also, of course, how to reach me. But other than that, I think we are time for the final suspend. So do we have any questions?
Just one thing, and that's the whole problem seems very similar to Windows executable loadings. So if you kind of had the inside info of how Microsoft does that, it has to recursively load DLLs and satisfy all the references, and also kind of deal with DLLs that are load suspended, so that they don't immediately load. But it's analogous. So you could actually, if you had the source code for that, you could kind of look at it and compare in parallel and say, yes, I'd like to do it this way.
Not sure if I caught all of that. What was the actual problem?
Nothing. It's just that your coroutines are kind of analogous to DLL loading. That's all. And executable loading.
Yeah, so in this case, I used coroutines to transform from the depth first or breadth first, so that we could batch. Obviously, that's not the only thing they're useful for. It's an application. There are many, anything where they're going to be doing stuff async like that. And this is all on a single thread. I should have pointed that out, by the way. There's no threading involved at all here. But we sometimes get the illusion of it. But even if you throw threads in, there can be a way to add parallelism to your concurrency. And you can actually hide all of the complexity of the threading in the infrastructure layer. And if you do it right, of course, out of the way of the application level code. It can actually work out very cleanly. So that there's different use cases that will have their own benefits, their own trade-offs. I wanted to show an example where you can actually see a clear benefit from using coroutines once you've established how complex the problem is. But it's not the only one by any means. So yeah, thanks for that.
It looks like, I mean, I didn't really quite get where was the waiter here, because it looks like it was automatically generated, and that's the only waiter you have, the one that is generated out of the dependencies.
So when co-await was called, that results in a wait transform being called on your promise type. And it gets past the dependencies that you're waiting on. A wait transform, which is code that we've written, creates a dependency awaiter. That's the thing with the awaiter interface, await ready, await suspend, await resume. So the only magic part in that sequence was getting from co-await being called to await transform being called. And the compiler generates that part for you. But the rest of it was just our code. That produces the dependency awaiter. And that's what then gets called back on those points. Does that answer your question, or was there something else I missed?
Yes. Yes.
Yeah, thank you. Yeah, that's what's often tricky with this. Even though I showed that, there's just so many moving parts and little magic bits going on. You've got to keep track of it all in your head. So, yeah.
Does it work? I think you showed it breaking.
Oh, yes, I should have fixed that problem and shown it did work. If I take this out and here. So we're now passing it by value instead. And it all works. Runs in basically the same time as before. So yeah, thanks for calling me on that.
You do a sleep in your coroutine. So that is a blocking call. And then that is just to simulate the actual time that it takes to read from the network. Mm-hmm. So you still do a blocking network call inside of your coroutine.
And that's another way that we could have used coroutines to do some other work while we're waiting for it. Obviously, at this scale of the problem, there wasn't really anything else useful we could do. In the real version, years ago, without coroutines, but doing the same sort of async stuff, we found the best level of parallelism was we would divide our problem graph up into smaller graphs, and then we will load one, and then while we're waiting for the network on that one, we'd start building the next one, and we'd like cycle between waits and computes that way. That's the trouble with parallelism and concurrency. It always depends on the problem at hand, how best to split it up. There's not that I know of, at least a one-way.
Yeah, but that would be exactly my question, because in the async version with the callbacks, there you typically have, for example, ACCU or whatever. So there you can actually do some other work while you are waiting for the things. So that might actually be faster.
What the coroutines does give you here is that point where we are waiting. We are in that infrastructure layer rather than at the application layer. Which means if we think, oh, there's something else we could be doing while we're waiting, we can put that on a separate thread or whatever, have I/O completion ports, whatever the mechanism is, we can do that at the point that we are coordinating all these coroutines. Now, I've only showed like one coroutine at a time here, the simpler case. actually it was a coroutine within a coroutine, but that's something else. If you have multiple coroutines, each of which can make progress at different times, there is a way to hand off control between them as well, which if you don't need any instrumentation in the meantime, you can do something called symmetric transfer, where it only goes out to the compiler level, compiler generated level, and back in again. And that's where that different return type for await suspend comes in, which I didn't show because it's a little bit more involved. And I don't remember all the details off the top of my head now, but there's quite a lot you can do there to really take advantage of your utilization. The point of this exercise was not to show what you can do while you're blocking, but just to minimize the number of blocks. But yeah, you can definitely do a lot more. Thanks.